Hello students. So in electronic circuit analysis and design subject, in this class we are going to discuss about the JFET small signal amplifiers. So first of all, I will give you small introduction about the JFET. Thereafter we can enter into the different JFET amplifier configurations. So in the small signal analysis of JFET, I am just giving you the brief introduction. JFET is a short form of field effected transistor. Okay, so the field effected transistor amplifiers provides an excellent voltage gain with added feature of high input impedance. So why we are going for the JFET means the JFET will gives you the excellent voltage gain with high input impedance. Okay, so when you compare with BJTs, the JFET will gives you the excellent voltage gain. The JFET will gives you excellent voltage gain and which has a very high input impedance. That is a main advantage of using the JFETs. So they are also considered low power consumption configurations. That also takes a low power from the supplies like VCCs and a very good frequency range and a minimal size and weight. The frequency range of JFETs are more than the BJTs and they are very less in size. The size of the JFETs are very less and the weight of the JFET is also very less. So because of these features, we are going into the JFETs instead of BJTs. And the both JFETs and depletion MOSFET devices can be used for designing amplifiers having similar voltage gain. So if you use a JFET or MOSFET, so we can get the same voltage gain. The voltage gain will be same. Okay, so we can also use the depletion MOSFETs or JFET for designing the voltage amplifiers. And also we already know the JFET is a voltage control device. Okay, the depletion MOSFET circuit however has a much higher input impedance than the similar JFET configuration. Okay, so as the depletion MOSFET and JFET both are giving the same voltage gain, but when we go for the depletion MOSFET means whenever we require very high input impedance than the JFET, then we will go for the depletion MOSFET. Okay, so otherwise we can go for JFETs. Okay, so these JFETs are divided into two types. One is a N channel JFET, another one is a P channel JFET. In N channel JFET, this is the symbol and this may also sometimes write like this. So these two are N channel JFET symbols and these two are the P channel JFET symbols. Okay, so what is the difference between the N channel JFET and the P channel JFET is the arrow mark on the gate. If it is going into the JFET, then that is called as the N channel JFET. If it is going outward, then that is called as a P channel JFET. Okay, there is a main difference between the N channel JFET symbol and the P channel JFET symbol. Okay, so in our circuits we are going to use this symbol instead of this. Okay, so let us see. The small signal model of a common source FET amplifiers can be used to analyzing the three basic FET amplifier configuration. So if you see there, JFET has a three pins, that is a gate terminal and source terminal and drain terminal. Okay, so based on these three terminals, we can able to get the three types of amplifier configurations. Those three types of amplifier configurations are the common source amplifier configuration and common drain amplifier configuration, which is also called as source follower, and the third one is a common gate amplifier configuration. Okay, so among these, the common source amplifier is the most widely used amplifier configuration because it provides a very good voltage gain. Okay, so I will tell you when we use this configuration with an example. So the common source amplifier short form is CS, and which will be used when we need the good voltage amplification, like the CE amplifier in the BJT. We have CS amplifier in JFET, and the CD amplifier, which is called as a which will be used when we need the buffer amplifier. So the buffer amplifier will provide you very high input impedance and a low output impedance. So that can be done using the source follower. Okay, like that the CC amplifier or emitter follower in our BJT. In JFET we have CD, the common drain amplifier configuration, and the third configuration, which is the common gate amplifier, will be used for high frequency amplifications. Okay, when we need very high frequency amplification, then we will go for the common gate amplifier configuration. Okay, so this is about the brief introduction about the JFET. In this we are going to discuss one by one the common source amplifier, common drain amplifier, and common gate amplifier. These three we are going to discuss. Okay, first of all, I am going to give you the small signal equivalent circuit of the JFET. Like we have the 3 or 4 types of equivalents for circuits for the BJTs, like R parameters, hybrid pi parameters, and the H parameters for the BJT. Similarly, the JFET is also containing one equivalent circuit, which is called the small signal equivalent circuit or AC equivalent circuit. So this is the N channel JFET. For this is a small signal equivalent circuit. So in the small signal equivalent circuit of the JFET, we have only the two components. One is a VGS current source, and RD, which is a drain resistance, internal drain resistance. As I already told, the input resistance of the JFET is a very large, so which is approximately equal to infinity. Therefore, the input side we don't have any component in the equivalent circuit. Okay, so in this equivalent circuit we don't have any components at the input side. Okay, so just we are going to mention the VGS voltage between gate to source, that is the input voltage for our JFET. At the output side, VGS is a current source. Okay, where GM is called as a transconductance gain. Okay, so the GM is the transconductance gain and VGS is the input voltage. So this is a dependent current source. Okay, it is depending on the input voltage VGS. That's why we are giving that the JFET is a voltage controller device. The input voltage VGS is controlling the output current. Okay, the input voltage VGS is controlling the output current. Okay, so the RD is the internal drain resistance which was connected between the drain terminal to the source terminal. Okay, so this is how we have to draw the small signal equivalent circuit of JFET. So wherever we have in the JFET in the circuit, that will be replaced with this equivalent circuit. Okay, so this equivalent circuit is containing only the two components. Okay, so only VGS at the input side, so gate to source is the input, so the voltage between gate to source are represented with VGS, and at the output side we have VGS source along with the RD drain resistance, internal drain resistance, which is in parallel with the VGS. Okay, so the input voltage is VGS and output current is mentioned as ID current. Okay, ID, which means that drain current, and output voltage was mentioned as VDS, the voltage between drain to source. Okay, this is the small signal equivalent circuit for the JFET. Now we are going to see the small signal analysis of JFET. The drain current of the FET depends on both gate and source voltages as well as the drain to source voltage. So in order to get the drain current ID, okay, so which is depending on both gate to source voltage as well as the drain to source voltage. So it is depending on the both gate to source voltage and drain to source voltage. It is not only depending on the VGS, it is also depending on the IDS, so that we can mention the ID is a function of VDS and VGS. Okay, ID is a function of VGS and VDS. Now therefore we can write the delta ID, the change in the drain current, which is equal to the delta ID by delta VGS into VGS plus delta ID by delta VDS into delta VDS. we can write like that, and then we can give the delta ID by VGS. ID is the output current, drain current divided by this input voltage VGS. Okay, ID by VGS, output by input. Okay, output by input, that is nothing but a gain. Here output is a current and input is a voltage, I by V, so which gives you the conductance GM. So that was mentioned here, and we have VGS, and here ID is the drain current at the output side and VDS is the output voltage. Okay, so here also this is I by V, but I current is also output current and this VDS is also output voltage. So that I by V, which will give you the output conductance. So that is nothing but represented with 1 by RD, where RD is the output resistance, that can be represented as 1 by RD here. Okay, 1 by RD into VDS. That is the drain current equation. ID is equal to GM VGS plus 1 by RD into VDS. Okay, that is the drain current equation. Let us see about the common source JFET amplifier. Okay, so this is the circuit for the common source JFET amplifier. So let us see, the VIN is the input voltage for the common source JFET amplifier. So why how we can say it is a common source means the source terminal of this amplifier has been grounded directly, so we can say it is a common source amplifier. This source terminal is common for both input side circuit as well as the output side circuit. Okay, so the input side gate is the input and output is the drain terminal. Okay, gate is the input terminal and drain is the output terminal. From the gate to source, we are giving one biasing resistor, that is called RG. So where RG means gate resistance, and there is the input voltage which is between the gate to source, which was represented with VGS, where VGS is the gate to source input voltage, and there is a drain resistance RD which was connected between the VDD supply, DC supply, and the drain terminal of our JFET. Okay, so ID is the drain current which is flowing in RD resistor, and we are going to take the output voltage across the drain and source terminals, so which was mentioned as voltage between drain to source, VDS. Okay, so this is about the different components in the CS JFET amplifier. Now we are going to draw the AC equivalent circuit for this common source JFET amplifier. This is the common source JFET amplifier AC equivalent circuit. So in order to draw the equivalent circuit, first we have to draw the common line. Okay, so first we have to draw the common line like this. Okay, thereafter, see, first we are going to draw the common line here. This one, source line is the common line, and the input signal VIN is directly mentioned here. Input signal VIN is directly mentioned, and the input terminal for this amplifier is gate, which was mentioned here. Output terminal is the drain terminal, so which was mentioned here. Okay, thereafter at the input side we don't have any component in the equivalent circuit of the JFET. We don't have any equivalent component, so we are just mentioning it with VGS voltage. The VGS is a voltage which was connected between the gate to source. VGS voltage just we have mentioned. Okay, and there is a resistance RG which was given between the gate terminal to the source terminal. So as it is the gate line, so we have added the RG and source here. Okay, which was added between the gate terminal to the source terminal. RG was mentioned, and at the output side of the JFET we have GM VGS source along with the RD drain resistance, So from the drain terminal to source terminal we have added GM VGS, and in parallel with the GM VGS we have added the RD internal drain resistance from the drain to source like this. And as we are doing the AC analysis, So we have to ground all DC sources to the ground. Therefore, the VDD has been grounded. Therefore, this drain resistance RG, which was in between the drain terminal to the ground terminal. So RD was mentioned from the drain terminal to the ground terminal, which was source. Okay, so like that we have to draw the common source JFET amplifier equivalent circuit. Now we are going to get the three parameters of the common source JFET amplifier: voltage gain, input impedance, and output impedance. Okay, so from the above circuit we can write the drain current equation. ID is equal to what? GMVGS plus VDS by RD. ID is equal to, so the drain current at this node, the drain current is splitting into two currents. Okay, the total drain current ID is splitting into the two currents. One is a GMVGS current, another one is a current flowing in the RD resistor. Okay, so the voltage at this node is VDS, so that's why ID is equal to GMVGS current plus the VDS by RD. So like that we have written the ID current equation. Therefore, if you multiply, if you take a RD as LCM in this right hand side, and we can take the RD to the left hand side, therefore which will gives you ID RD. So GMVGS RD plus VDS. Okay, so we have taken LCM of RD, and then we have taken the RD to the left hand side, which will become IDRD GMVGS RD plus VDS. Okay, now so the above circuit can be redrawn as, so here if you see, this circuit can be redrawn like this. How we can redrawn means, there is a current source with a parallel resistance which can be replaced with a voltage source with a series resistance. Voltage source with series resistance. Here if you see, this IDRD plus GMVGS RD plus VDS we have. So what is this GM into RD means? That is nothing but mu. Okay, where mu is equal to GM into RD. Okay, therefore we can take this VDS is equal to IDRD, and we have taken this GMVGS to the left hand side, so which becomes minus GMRD. So VDS is equal to IDRD minus GMVGS into RD, and as I told, we can take the mu is equal to GM into RD. Therefore, we have IDRD plus minus mu VGS. Okay, that is what the drain to source voltage value. And similarly, this circuit can be redrawn using this voltage source, where mu VGS is a voltage source. Okay, so this Norton's equivalent circuit has been converted into the Thevenin's equivalent circuit, and the mu VGS is a voltage source and RD is a drain resistance which is series with this source. Okay, so here mu is a voltage source which is equal to GM into RT. Okay, so in our analysis, for simplification, we have taken this equivalent circuit in terms of the voltage sources. Okay, so this is the equivalent circuit. Now we are going to get the input impedance. So input impedance is the ratio of input voltage to input current. But here if you take, so the input resistance was given as the resistance seen from the input side of the JFET. Okay, so if you see from the input side of the JFET, we have only one resistor, that is the RG. We have only one resistor, that is RG, that is equal. Therefore, we can say the input impedance will be equal to the RG. There is no resistance here. Here we have the infinite resistance. So infinite in parallel with RG, we can get the equivalent resistance of RG only. Okay, the input resistance is a very large for the JFET. So that we are using one RG resistance in order to make it as finite value. Okay, so infinite in parallel with RG, we can get RG as input resistance or input impedance. Similarly, we are going to get the output resistance of the JFET amplifier. Okay, so the output resistance is measured at the output terminals when Vi is equal to 0. So if this Vi in is equal to 0, then VGS is also equal to 0. Okay, so output resistance will be measured only when the input voltage Vin is equal to 0. As the Vin is equal to 0, VGS also will be equal to 0. So this VGS, mu VGS voltage source will also be equal to 0 here, because it is depending on the input voltage VGS, mu VGS. So here VGS is equal to 0, therefore mu VGS is also equal to 0. Therefore we can say at the output side we have only the two components RD, which is in parallel with the capital RD, the external drain resistor, in parallel with the internal drain resistance. Okay, so the output resistance is the resistance looking into the amplifier from the output side. If you see from output side, we have only the two components here, RD in parallel with the RD. Therefore, you can say output impedance of the JFET amplifier, CS JFET amplifier, which will be equal to RD parallel RD, small rd parallel the capital RD. Okay, so this is how we have to calculate the output resistance. And the third parameter we are going to calculate is the voltage gain. So what is voltage gain? The voltage gain is the ratio of output voltage to the input voltage. Here output voltage is VDS and the input voltage is VGS. Okay, so we need to get the ratio of output voltage to the input voltage. Therefore, AV, the voltage gain, is equal to VDS divided by VGS. So okay, so here the VDS, the drain to source voltage, was given as applied voltage into across the resistance divided by the total resistance. So here this is a negative voltage, that's why we have taken negative here. So because the direction of the current is opposite here. Okay, so mu VGS minus mu VGS is the voltage applied in this loop. Okay, and then we have to get the voltage across RD. So that's why RD, okay, applied voltage into across the resistance divided by the total resistance in this loop. So here we have only the two resistances, one is RD, another one is the capital RD, therefore RD plus RD. So like that we have to get the VDS value, output voltage value. Therefore from this equation actually we need to get VDS by VGS. The VGS is available in the right hand side. If you take the VGS to the left hand side, the VDS divided by VGS we can achieve. Therefore AV is equal to, so which is nothing but VDS divided by VGS, that is the voltage gain of this JFET amplifier, which is equal to minus mu RD divided by RD plus the capital RD. Okay, minus mu capital RD divided by RD plus RD, that is the voltage gain equation for the common source JFET amplifier. Next we are going to see one problem regarding the common source JFET amplifier. So in this problem, in the CS amplifier shown in the figure, RD was given as the 5 kilo ohms and RG gate resistance was given as the 10 mega ohms and mu was given as 50 and the drain resistance RD was given as 35 kilo ohms. Therefore, we need to get the voltage gain, input impedance and output impedance of the circuit. So I have drawn the equivalent circuit for the CS amplifier. From this we can get the V0 is equal to minus mu VGS RD by RD plus RD, and the VGS is the input voltage, which is nothing but VI here. The voltage gain is equal to what? V0 divided by VI, which is nothing but V0 divided by VGS. So here mu RD by RD plus RD is the equation. So here I am substituting the mu value which was given as 50 into RD value is 5 kilo ohms, which is 5 into 10 to the power of 3 divided by the capital RD plus small rd. The capital RD is 5 into 10 to the power of 3 and the small rd is equal to 35 kilo ohms. So after substituting the values, we can get the voltage gain as minus 6.25. Minus 6.25, that is the gain of this CS amplifier. So next we need to get the input impedance and output impedance. We already know the input impedance is equal to the RG value. So the RG value was given as 10 mega ohms and already we know the output impedance is equal to the small rd in parallel with the capital RD. The small rd value is a very large value when compared with the drain resistance RD. So the resultant of RD parallel RD is equal to the capital RD only. Therefore we can say this 35 kilo ohms in parallel with the 5k approximately equal to the 5 kilo ohms. Okay, that is the output impedance of the CS amplifier. Okay, so in the next class we are going to see about the common drain JFET amplifier.